How to get the Jacobian matrix for an isoparametric element? Let us discuss in this lecture video with the problem. Evaluate the Jacobian matrix for the linear quadrilateral element as shown in the figure. The coordinate positions of the quadrilateral element are mentioned in the figure, but at which point the Jacobian matrix has to be obtained, that detail has not been mentioned in the problem. So by keeping that local coordinate position epsilon and eta as variable, we need to formulate the Jacobian matrix. Okay, the Jacobian matrix for the isoparametric element is a 2 cross 2 matrix, that is J11, J12, J21, J22. It can be also represented as J11 is dou x by dou epsilon, J12 is dou y by dou epsilon, J21 is dou x by dou eta, J22 is dou y by dou eta. For quadrilateral element, the Cartesian coordinate positions can be calculated using the formula x is equal to n1x1 plus n2x2 plus n3x3 plus n4x4. Here x1, x2, x3 and x4 are the x coordinate positions of the nodal points. n1, n2, n3 and n4 are the shape functions. Similarly, y coordinate position formula is n1y1 plus n2y2 plus n3y3 plus n4y4. So the shape functions formula for an isoparametric elements are known to be n1 is equal to 1 by 4 into 1 minus epsilon 1 minus eta, n2 is 1 by 4 into 1 plus epsilon 1 minus eta, n3 is 1 by 4 into 1 plus epsilon 1 plus eta, and n4 is 1 by 4 into 1 minus epsilon 1 plus eta. Here epsilon and eta values are not given in the problem, so we can substitute the shape functions values like this itself. In the formula of x coordinate position, this is n1, this is x1. So n1 x1 plus this is n2, this is x2. Okay. Then this is n3, this is x3. Then this is the formula for shape function n4, this is x4. Now we can expand the terms. That is, in the first term, 1 minus epsilon into 1 minus eta is 1 minus eta minus epsilon plus epsilon eta. In the second term, 1 plus epsilon into 1 minus eta is 1 minus eta plus epsilon minus epsilon eta. Similarly, this is for the third term and this is for the fourth term. We can simplify this step by grouping the coefficients of the eta, epsilon, epsilon eta and the constant term. First, considering the constant terms, in the first term, the constant term is 1 by 4 into 1. In the second term, 2 by 4 into 1. In the third term, plus 2.5 by 4 into 1. In the fourth term, this is 1.5 by 4 into 1. So then the constant value can be obtained as 1.75. Next, considering the coefficients of eta, in the first term, the coefficient of eta is minus 1 by 4. In the second term, the coefficient of eta is minus 2 by 4. In the third term, the coefficient of eta is 2.5 by 4. In the fourth term, the coefficient of eta is 1.5 by 4. By grouping all the coefficients of eta, it will be 0.25 eta. Similarly, considering the coefficients of epsilon, we can get this 0.5 epsilon. Okay. Similarly, considering the coefficients of epsilon eta, we can get this 0 epsilon eta value. Now we have the x coordinate position expression like this, from which we can calculate dou x by dou epsilon and dou x by dou eta values. Okay, dou x by dou epsilon is nothing but partial differential form of this x expression with respect to epsilon. The partial differentiation of the constant value 1.75 is 0. While differentiating the second term 0.25 eta with respect to epsilon, we will get 0. Then partially differentiating the third term 0.5 epsilon with respect to epsilon, we will be obtaining this term 0.5. This is 0. Okay. So the dou x by dou epsilon value can be obtained as 0.5. Similarly, dou x by dou eta value, so in the x expression, eta va poruthu partial differentiate pannom appadina 1.75 ku differentiation 0, 0.25 eta va poruthu differentiate panna 0.25, 0.5 epsilon ஈட்டாவை பொறுத்து differentiate பண்ணா partial differentiate பண்ணும்போது 0. So the dou x by dou eta value can be obtained as 0.25. Then considering the y coordinate position formula, this is n1 y1, this is n2 y2, this is n3 y3, and this is n4 y4. Okay. In the first term, y1 is 0, so n1 into y1 becomes completely 0. Similarly, in the second term, n2 into y2, y2 is 0, so the entire term will be 0. Okay. In the third term, we can expand this 1 plus epsilon into 1 plus eta as 1 plus eta plus epsilon eta. In the fourth term, we can expand this 1 minus epsilon into 1 plus eta term as 1 plus eta minus epsilon eta. Okay. In the next step, we can group the constant values and the coefficients of eta, epsilon and epsilon eta. We can get the simplified expression for y coordinate position as 0.625 plus 0.625 eta plus 0.125 epsilon plus 0.125 epsilon eta, from which we can calculate the values of dou y by dou epsilon and dou y by dou eta. First, partially differentiating this y with respect to epsilon. The partial differential form for this constant value 0.625 is 0. 0.625 eta epsilon பொறுத்து differentiate பண்ணோனா 0. 0.125 epsilon பொறுத்து differentiate பண்ணா 0.125. 0.125 epsilon eta epsilon பொறுத்து differentiate பண்ணா 0.125 eta. So dou y by dou epsilon value will be 0.125 plus 0.125 eta. Next, partially differentiating the y coordinate position expression with respect to eta. First term differential form 0. Second term, that is 0.625 eta பொறுத்து differentiate பண்ணா 0.625. Third term 0.125 epsilon eta பொறுத்து differentiate பண்ணா 0. Fourth term 0.125 epsilon eta பொறுத்து differentiate பண்ணா 0.125 epsilon. So dou y by dou eta expression will be obtained as 0.625 plus 0.125 epsilon. Okay. Now we can substitute all the calculated values in the Jacobian matrix formula. Then the simplified Jacobian matrix will be obtained like this.